Good morning everyone, and welcome back to the second video of the Beginner's Guide to the Power Sector series, where today we'll be talking about the wondrous world of power generation. Now, we all take advantage of the ability to plug our phones in before bed and wake up in the morning to a charged phone. But today, we are really going to be looking into how that power that charges our phone is actually generated specifically within Australia. Now, as I iterated in my past videos of this series, which I'll link in the description below, my absolute goal of this series is to provide you context about the power sector so that you can go ahead and have conversations with your friends at school or uni, family members, or even industry representatives at things like conferences or career expos. Because I believe in the power sector, once you have a certain level of context around things like generation, transmission, distribution, and the whole kind of power sector, going to those industry events is an absolutely awesome way to expand your baseline knowledge. It's just a matter of finding that baseline knowledge. So my primary goal of this series is to provide you with that baseline knowledge. So as I said, today we're going to be talking about generation. So I'm going to hop on my computer and we can get straight into the presentation. Alrighty, so generation, which, as you can see by this diagram here, is essentially the root of all things power in Australia. Essentially, without generation, we wouldn't be able to plug in our phones and charge them overnight. We wouldn't have anything. Generation is essentially, as I have here, the process of producing electricity. So if we don't have generation, we can't produce electricity, and therefore the rest of the network is essentially useless because we don't actually have that electricity to transmit, distribute, or consume. Alright, so today we're going to be talking about four key areas. So the first one we're going to go over is Australia's generation mix. Essentially, what sources of generation mixed together and used as our electricity supply in Australia. The second part will be going through the three different methods of generation and the three different classes. The third type will be how these classes of generation connect to the grid. And the fourth will be a future outlook, essentially looking ahead into the future and trying to profile what our generation mix will look like 10, 20 years in the future as we progress through the energy transition, and what mixture of our generation methods will allow us to not only reduce our greenhouse gas emissions, but still be able to supply our peak demand. So to start off, I thought I'd give a bit of history of generation in Australia. So the first major milestone was the first power station in Australia, which was a coal-fired power station commissioned in both Sydney and Melbourne in the late 19th century. Following that, in 1985, the first hydro station was commissioned, called the Duck Reach Power Station in Tasmania. So this was a run-of-the-river type hydro station, kind of like the little cartoon pic there. Following this hydro station was the expansion of generation in Australia. Now, this occurred mainly due to the Industrial Revolution in the 20th century. Now, because of the modularity of coal, it was mostly coal-fired power stations, and they were commissioned across Australia. So mostly where the main load centres were, but also in the industrial areas, such as mining towns and things of the nature, which really started to ramp up with the industrial age. Now, the fourth milestone is what I like to call the dawn of the renewables. So in 2001, a renewable energy target, or the RET, was commissioned, which essentially encouraged both residential and industrial consumers to take up more renewable energy. Now, this was mostly solar and wind, and really kickstarted that sort of uptake in Australia. Now, the fifth milestone, or where we are now, is essentially the energy transition, where the phasing out of fossil fuels has really started to accelerate. We see a lot of decommissioning of the old traditional coal-fired plants and retrofitting with newer, cleaner technologies, but also the increased reliance on intermittent solar and wind energy to really lead the charge and supply most of our electricity. So from that first power station through to the energy transition, this is essentially our past 200 years. So you're probably wondering, what does Australia's generation mix look like now? So in the last video on the Australian power sector overview, I really gave a bit of a demo on AEMO's website and the resources available there. So if you're interested more in how I got this figure, check that video out. But this figure here shows two things. So the top section of this figure, the column chart, that shows the consumption of the NEM, or the National Electricity Market, over the past 12 months. So As we can see by the black column, which is coal, that generates approximately 49% of our electricity consumed in the NEM, followed by brown coal, which is 17%, wind, which is 10%, and then solar, which is 9%. So they're kind of the four big players still. But now the bottom part of the chart actually shows a specific day and time. So this actually shows the 29th of February and the specific generation mix for 12 to 1 p.m. on the 29th of February. So it shows the clear split of generation sources. So as you can see here, again, black coal leading the charge with 45%, but around midday being the peak time for solar, we can see solar is generating 27% of the demand here, wind is producing 8%, and brown coal producing 15%. So a pretty good contribution from renewables. But further analysis of this can, divide these energy sources into three different categories. So what we've got first is firm energy, being biomass, black coal, brown coal, natural gas, and liquid fuel, being some diesel generators most likely. Our variable energy comes from a selection of biomass plants, some hydro energy, other being some sort of batteries, etc., solar and wind. And then our storage, which is the third type, being mostly batteries, but there's also different chemistries, which I'll cover later. So a way we can think of the generation mix is essentially using a water tank. So once all of these generation sources are connected to the grid, they essentially act as one big stream of water flowing into a water tank, which from there, customers can tap into and pull as much water out of that tank as possible. But what we've kind of got to conceive is that the collective flow flowing into the water tank needs to be greater than the collective demand from the customers out of the tank. Otherwise, that's going to cause significant damage to things like voltage and frequency, which, if there's an imbalance in supply and demand, are impacted by. So, as we covered in the last slide, there are three main types of generation. The first being firm generation, which is akin to our traditional power generation, like coal-fired, gas-fired, and diesel generators, for example. They can be turned up and down as required. The second type is variable generation, which is very akin to our renewables. They're called variable because they're very dependent on the weather. So if the sun's out, solar's generating a lot, that's fine. If the sun's not out, solar's not generating. So that kind of variable nature is why it's called variable or intermittent generation. And then the third type being energy storage. So energy storage, like its name, means that it can charge and discharge as required by the market operator. So it's called grid embedded because otherwise it wouldn't be able to connect into that supply and act as an in-feed to our tank, harping on the last analogy. So firm generation is essentially the ability to produce constant electricity. Firm, as a definition, essentially relies on constant fuel sources and it's unaffected by weather conditions. Fuel sources such as fossil fuels, being crude oil, coal, anything that can heat water and push it through a turbine is essentially firm. Firm was also referred to as the flexibility to scale power output up or down as required by the market operator. So essentially, the market operator is best friends with the firm generator. Because if there's an influx of demand, the market operator essentially rings up the generator and is like, oh, okay, can you double your output for the next 20 minutes? Firm generator says, okay, sure, we're going to charge you a lot. The market operator says, I don't care, I need you to supply my demand. They hang up the phone and crank up their turbines, essentially, if they have the capacity, of course. But another characteristic of firm is that they provide the base load power. As I said before, ensuring consistent power supply. Now, specific characteristics here is that they have high greenhouse gas emissions due to their reliance on fossil fuels, as well as they're expensive to source these fuels because obviously mining's pretty expensive to get up things like crude oil and coal, and the deposits of these sorts of things are only getting harder to access, so elevating the price. Specific grid capabilities of firm generation, they provide a black start capability. Because they're rotational machines, they can start from essentially no input. They don't need an external force to essentially kickstart them, so they are able to provide black start functionality as well as a capability called system inertia, meaning that essentially if another load is connected to the grid, because it's a rotational machine, they can essentially spin faster to be able to generate more and cater for that increased load without inhibiting things like frequency. So moving on to what we call variable energy, which is essentially producing intermittent power relying on weather or other conditions. In Australia, we essentially rely on three different ones, being solar, which gets its energy from the sun, wind, which gets obviously its energy from wind turbines spinning in the wind, and the third being hydro, frequent in Tasmania, as I said in the history, but they can either be run of the river or pumped kind of storage. I also included tidal here because as Australia is an island, it's only going to be more frequent in the future. Now, characteristics here are that they are cheap and readily available fuel sources because they're all natural. Things like solar and wind, of course, you get pretty frequently in Australia especially. They're significantly reduced greenhouse gas emissions due to the natural fuel sources, like the sun and wind kind of blow as is, and using solar and wind is very efficient and effective in terms of carbon emissions. However, they're very characterized to certain geographies. So things like geothermal in Norway, because the Earth's core is very close to the surface there, they can use geothermal, whereas in Australia, that's not applicable. But what we have here is a very hot climate, which is obviously akin to a lot of solar, being sunlight and wind. So grid capabilities for variable energy, they provide a service called FCAS, which is essentially frequency control and ancillary services. So say something happens in the power system and they need a big influx of electricity or a speed up in electricity. Something like a wind turbine or a solar system may potentially be able to ramp up, maybe not as rapidly as something like a battery, but ramp up and supply that prolonged FCAS. They also have abilities with new grid forming inverters to be able to, generate their own AC waveform, but that's something that's still being developed and is more akin to batteries. So the third type of power generation is what we call energy storage, which is the process of capturing and storing energy for later use. Now, the primary use case here is something called arbitrage, where batteries essentially capture the excess generation in periods of high supply and low demand, and then discharge this stored energy in periods of low supply and high demand. So essentially being able to take that high supply of PV during the middle of the day and store it until it's required later in the day when everyone gets home and the sun goes out, so around 5-6 p.m. in winter. Now, there's many types of storage, some widely adopted in Australia, things like BESS, so battery energy storage systems of different chemistries, as well as pumped hydroelectric storage. So essentially how they work is that they need to be by a water source. They pump that water up the hill in periods of high supply and low demand. And then when the energy is needed, they run that water down through a turbine and generate electricity. So again, using that arbitrage characteristic. So some other battery technologies in development at the moment are things like thermal energy storage, gravity energy storage, compressed air energy storage, and hydrogen, which is a hot topic in South Australia at the moment. Essentially what hydrogen allows us to do is when we have that high supply of, say, rooftop PV, what we can do is we use that high supply of energy to essentially electrolyze water into hydrogen, which can later be used as a gas to turn a turbine, just like steam does. So it's an efficient way of storing that excess energy in the medium of hydrogen gas, which can then be used later to generate electricity. So characteristics of energy storage, it's characteristically very expensive, and some technologies rely significantly on topography. So for example, a pumped hydro storage needs to be right next to water to be able to pump it up and down. So although it's very cheap, we can't apply everywhere because we obviously don't have water in the middle of Australia because it's very dry. Whereas batteries are very expensive, but they're modular, so essentially they can be installed anywhere there's capacity on the transmission network, but they're very expensive. So you kind of got to weigh up your options here. Grid capabilities of energy storage, we've got FCAS again, as well as grid following and grid forming with the new inverter. So with the Dalrymple battery that's just been installed on the right here, but over on the Yorke Peninsula, that actually has inverters that allow grid forming. So if the Yorke Peninsula gets islanded, this battery actually is enabled to be able to generate its own waveform and synchronize with the existing grid over there, which is pretty cool. So if you're curious into grid following and grid forming inverters, I encourage you to do some more research. They're awesome little pieces of technology. So now that we've gone over the different generation methods, you're probably wondering, how does this generation actually get to the network? So this is through means called grid connections. So Despite the generation type, all different variations essentially stem from a thing called a switchyard, which is essentially an internal substation usually owned by the asset owner, whoever owns the generation. So what I've done is kind of divided it into the 3 different generation types and kind of the stereotypical layout for each. So let's start with firm generation. So how these work essentially is that the turbines get collated into what I've called a collection bus, which, because they have AC outputs, they can then be put straight into a step-up transformer, which steps the operating voltage up to that of the transmission line connection, which can then be exported to the grid. For renewable generation, I've shown examples of both solar and wind. So for solar, we would have strings of panels which output DC power going through a DC to DC converter to essentially synchronize the voltage. This DC power is then put through a DC to AC inverter, alike but much bigger than the ones you use on your rooftop system. This outputs AC power, which can then be stepped up using the same step-up transformer to transmission level voltages, which can be exported to the grid. A bit different with wind, because wind turbines actually output AC power. This AC power is put through an AC to DC inverter, which can synchronize the power again, and then put through a DC to AC converter to generate that synchronized AC waveform, put through a step-up transformer to transmission level voltages, and then exported to the grid. Now, energy storage is a bit different, as it must be able to support bidirectional flow, meaning that it has to be able to operate in both charge and discharge stages. So the charge stage, or essentially when we're pulling from the grid, we need to go from the grid through a step-down transformer to take it into manageable voltage levels, where we'll then go through an AC to DC inverter. Now, this is because DC is what is stored in batteries, and then the power then flows into the battery. To discharge, that DC power from the battery is put through a DC to AC inverter to put it into an AC system. This AC power is then stepped up using a step-up transformer to transmission level voltages, and then exported to the grid. So the discharge is essentially the same as renewable generation, but having that charge functionality is key. Now, this charge-discharge functionality can be essentially accomplished with the same infrastructure, but we've just got to make sure that the tap changer on the step-up/down transformer has enough range so that it can manipulate the windings on the high side and the low side to ensure that the voltages can be stepped down correctly. Now, additional requirements of these switch yards, there's 2 things. So the first being protection devices. So if there's a fault at any point in the switch yard, we've got to be able to switch around it to not damage the other equipment. So these can include things like circuit breakers, disconnector fuses, air brakes, etc. You're going to have CTs and VTs to monitor the power quality across the station. And the second thing is what we call SCADA devices. So SCADA stands for Supervisory Control and Data Acquisition. So it essentially provides communication and control functionality to the substation. So people from remote can see if there's a fault and then switch off or see what sort of fault it is, so they can send out the relevant people, for example. So that's essentially grid connection. Also, one more thing I'd like to note here is that transmission line connections are only required for the higher capacity generation plant. So the capacity of generation allowed on a certain line is essentially dependent on both the thickness of the conductor, but essentially the rating of the conductor. So if it's rated for a certain power flow, then you can export more electricity through it. If it's not, you can't export as much. So transmission line connection points are only required for the really big wind farms, really big solar farms, etc. So things like 200-300 megawatts. Whereas you can actually get away with a 33 or 66 kV distribution line for some of your smaller solar farms and batteries, for example. So again, it comes down to cost. So if you go into the whole effort of installing this big wind farm, you're not going to do it next to a distribution line, which will only allow you to export 10% of your capacity, for example. So being selective with that sort of stuff is always best when you're looking at grid connection. All right, so we've looked at history, we've looked at the generation mix, we've looked at generation methods, we've looked at how they're connected to the grid. You're probably wondering, how does this look like in the future? So the way I like to think about the future outlook of our generation mix is actually in terms of a soccer pitch, where we've got 3 key positions. We've got our forwards, midfielders, and defenders. Now, as our forwards, we want renewable generation. They're fast, they're flashy, and when they're performing, we want them to essentially win us the majority of our game because they're cheap and they're the most effective. But the trouble here is that when the sun's not shining and the wind's not blowing, what do we do with our energy? Essentially the same in soccer. When they've got good defenders on them or we can't get the ball to them, they can't win us games. That's when we have to rely on our midfielders. So our midfielders in this analogy are energy storage. Now they're our most reliable backups. They can provide short bursts of support to support our renewables while they recover or while they get their rest. Essentially, they can pick up the slack when our strikers or our renewables aren't performing. But the trouble here is that they're only short term. They only have a certain amount of storage capacity that they can supply until they're exhausted as well. And that's when we have to rely on our defenders. So our defenders in this example are what we call firm generation. They're our trusted and reliable power sources because they can essentially provide power as required. As I said before, if the market operator rings them up and asks them to generate more or less, they're okay with that. Essentially, they're our last line of defense. Things like black and brown coal are heavy polluters. So they can't be a massive part of the energy transition. But this introduces a technology called CCS, or carbon capture and storage. Essentially what it does is allows you to implement kind of like a catalytic converter for a car at the stack to capture most of the carbon released into the atmosphere to really mitigate the environmental impact from these traditional sources. Now, in Australia, we've tried to move away from coal and more toward natural gas as it's much cleaner. But in the future, our CCS is still going to apply to natural gas. So you're probably thinking, if I was to pick my team in the future, what would it look like? As the leader of my team, I want my intermittent renewables as solar, wind and hydro doing most of the work. I want them leading from the front, scoring as many goals as they can and knocking them games off. But when these guys get tired, I'm going to need a bit of backup. This is where that firm dispatchable backup comes in. Things like energy storage, which can store all my PV and wind from those high supply periods and really use that to meet the demand later in the day. But when my energy storage get tired, I need some clean, firm generation to really step up. Things like natural gas to supply that half an hour, 1 hour during the day where my renewables aren't generating and my storage capacity is all used up. I need them to really pick up the slack there. Taking this analogy further, I need a solid bench because although my first and second options are very reliable as a whole, I need things like hydro from hydro-friendly areas and wind from very windy states. I need to be able to transmit that energy from the periods of high supply, say in one state, to another state that's experiencing a state of high demand. And now this is where interconnection is absolutely key. Being able to take electricity from an area that is in a state such as high supply and transmitting that to, say, Melbourne, where the big load centers are during the day, is absolutely key to a balanced network. And it's only going to attribute to the harmonious operation of this team of the future throughout the energy transition. It's also important to identify that the teams won't look alike universally. So as I said earlier, Norway, 100% renewable, but only because they rely 100% on geothermal. Whereas this geothermal in Australia can't be applied because the Earth's core simply isn't close enough to the surface here. So we have to rely on things like solar and wind, which are akin to our climate. So being able to identify that and build our network accordingly is another attribute that we're going to have to continue with throughout the energy transition. So overall, generation in Australia is a very, very important thing. And as I said, without it, we wouldn't have anything we use every day. As a bit of a summary, the generation mix is essentially a mixture of generation connected to the network, acting as that stream to fill the tank which customers tap into. Now, the three key players connecting and feeding into this tank are firm generation, variable generation, and energy storage. Only with the combination of these three will we be able to generate electricity consistently throughout the energy transition. To create this flow into the tank, we need what's called a grid connection, which is essentially how the generation is connected to the electricity grid. Across the three different generation methods, they all use some variation of an internal switchyard, which is essentially a step up or step down transformer to be able to export or import from the grid. And lastly, our future outlook. What combination of our three generation methods are we going to take into our future? Now, continuing back to that analogy, we need a balanced sports team. One that can perform 90% of the time as a clean, effective team that meets all of our demand with renewable supply, but in that 10% of the time can really knuckle down and supply our demand with clean and firm generation. Essentially, we need to be prepared for all scenarios. So that's generation, an entire overview of how our power is generated in Australia. But you're probably thinking, how do we actually get that power to consumers? And the next step in that chain is what we're going to be covering next week in the video about transmission. Now, transmission is essentially how generation is transmitted those long distances to the significant load centres such as your capital cities like Melbourne, Sydney. If you look out of your windows in those areas, you won't see power generation stations. And that's normal because normally power is generated, as I said earlier, in those geographically friendly locations. So if you enjoyed today's session on generation and are keen to learn about transmission in next week's video, let me know down below. And otherwise, I'll catch you guys next week. Have a great day. Thank you so much for watching that video. If you enjoyed it and want to see a similar video on the channel, click right here to see the next video in the playlist. Otherwise, for the latest upload to the channel, click right here. As always, it's a great day to have a great day, and I'll catch you in the next one.